All right, guys, hello. How are you doing? How is the exam coming along? It's over. You are ready to submit it? Pretty much, yes. You remember that the exam is supposed to be on that form in one PDF file titled, like I mentioned in the instructions. Good? So that you will send in my email, and possibly I will see also through Blackboard. Good? But email will be certain I'll receive it, and Blackboard will be just maybe a redundancy. We'll see. The title instructions, well, they are in the exam. So when you open the exam, the first thing you see is instructions. So it should be P, last name, first name, and something else. You can just read it if you need to. We will talk about it. Right, guys? Don't disappear. Turn on the cameras if you can. Good. Thank you, Jack. And who else? Would be nice to see you guys. All right. All right. So I think we left off somewhere here. Remember, what we have is the situation where we have a sample space, but it's not immediately a sample space of interest. The sample space of interest is induced by collapsing the individual outcomes of the available sample space to the outcomes of interest and adding up the corresponding probabilities of the collapsed outcomes. Good. So you can think of it as conservation of mass, where the pebbles that are collapsed to a single event of interest will have their individual probabilities added up. And that is what a random variable is, nothing more. It's just a function from a sample space that can be used to induce, can be induced probabilities on another space S star. Good. So all that we have to have is that the function is onto. And we solved the first exercise here. So here is another example. A fair die is tossed until it comes up 6. Let X denote the number of required tosses. Yes. So how many? So we want to know, is it 1 toss or 2 or 3 or whatnot? So X takes the values 1, 2, 3, all the way possibly to infinity. We can see if infinity is possible here. So we can say probability that X is equal to 1 is 1 over 6. Probability that X is equal to 2 means that the first round was unsuccessful. We did not get a 6. And on the second round, we did get a 6. So it's 5 over 6 times 1 over 6. We can use here multiplication, since the rolling of the die do not affect the future outcomes, right? So what happened on the first roll does not affect what will happen on the next roll. So we can do that by multiplying probabilities. And in general, probability that X is equal to n, it's 5 over 6 to the power of n minus 1 times 1 over 6. And we can then verify that the probability that X is an integer, in other words, that it will take finitely many rounds until we get a 6. That's the probability that it will take either 1 round or 2 rounds or 3 rounds or however many rounds. It's the summation here. And that summation is a geometric series which is equal to 1, which means that the probability that X equals to infinity is 1 minus the probability that the game will stop. And that probability is 0. You understand? So the probability that you will never get a 6 as you play it is 0. And of course, the question you already know the answer to, does it mean infinity cannot happen? Does it mean that you will not have the situation? It's just not observable. In some sense, it's even a ridiculous question in terms of what you call real life, at least when you roll a dice. You always have to imagine that the situation can be made such that you can observe something. But definitely if you throw a dice, I mean, you're not gonna do it forever, it doesn't matter. Good. Now we talk about, very important is the category of discrete random variables. So those are random variables that take on countably many different values. They take real values possibly, but definitely countably many distinct values. Have you ever taken analysis, guys? Do you know what countably many means? It's not important for this class, not too important. It just means that you can list them as first, second, third, fourth. They have a one-to-one correspondence with natural numbers. That's what countable is. Good. There is a short video if you want to see it. You can find, just type something about infinity, or perhaps I will send you that video. It's probably no more than 8 minutes long, and that gives you a good sense of those ideas. So then, for countable variables, the individual outcomes x1, x2, x3, and so on. The fact that I indicate 1, 2, 3 means that I can queue, or I can put the values in a queue line from first, second, third, fourth. I can list those values, and those values are assigned a probability mass function. In other words, it tells you what's the probability of x1 happening, or x2 happening, or x3 happening. And of course, since one of those outcomes has to happen, the sum of them is equal to 1. Questions? You understand what I'm saying, guys? So not too fast. Random variable, right? So in this case, we have some sample space which we collapse to countable outcomes x1, x2, x3, x4, and the probabilities of each of those outcomes must add up to 1. You agree? Because each of the outcomes is induced by one outcome in the original sample space. Good. So when you say random variables, the word is a bit weird. All it is just a function from one set to another. Good. And we will see more examples. Here is one example. Here is a fair coin is tossed 2 times, and x denotes the number of heads obtained. Then here we graph the mass function. So we have the possibilities are either 0 heads, or 1 head, or 2 heads. So the probability that I get 0 heads, it's the probability of TT. So in other words, the event tail is converted to the probability of no heads, of 0, right, to this number. And that probability is 1/4. Now one head, it's converting the outcomes TH and HT. And we have 2 of them, they are 1/2. And the probability of 2, it's just, of course, also 1/4, like in the first event. Yes, you see what was the random variable truly doing? Just to illustrate, so when it's still simple, my sample space, my S, had these possibilities: tail, head, tail, and head, right? And what did my random variable x do? It's just only x only pays attention to the set S, right? It took those outcomes and it produces numbers 0, 1, and 2. So what happens is that this is carried to 0. This, one second, I wrote here. So this should be head. This is carried to 2, and these 2 are carried to 1. Yes, very simple. And what happens is that initially each had probability 1/4, but this has 2 1/4. So it's like 2 stones of the same weight were melted to produce this one, and so we have a 1/2 here, which is equal to 1/4 plus 1/4. and this one was 1/4. So that's exactly what we had preserved. Good. So you see how random variables are very simple, right? All they do is they just convert one sample space into another set, and that other set is induced sample space. Very simple. Let's see, let's begin with a basic example, guys. Suppose that the random variable can take numbers 0, 1, 2, all the way to infinity, all the non-negative integers, and the mass function is given as follows. Its probability of n is c times lambda to the n over n factorial, where c is to be determined in terms of lambda. Okay, so please tell me what's the value of c first and foremost. If this is the mass function, if you need this to be specific, imagine that p of n is equal to some c equal to 2 to the power of n over n factorial. So in general, instead of 2 is just consider lambda. This is given. So could you please tell me what is the value of c? Well, I presume the h is the lambda, yes? That's good. Yep, that's very good. So the value of c, easily obtained, guys. Simply, we know that the sum of the probabilities has to add up to 1 because we have a new sample space there. And what do we have then? We have that 1 equals to c lambda to the n over n factorial. I can factor out the c. What do I get here? It's c multiplied by e to the lambda. And that makes c equal to e to the minus lambda. And that allows me, now that I know c, it allows me to figure out what's probability where x is equal to 0. That simply is e to the minus lambda, lambda to 0 over 0 factorial. And that's the probability of 0. Probability where x is bigger than 2 can be obtained by taking 1 minus probability where x is less than or equal to 2. And that is 1 minus probability x is 0 or 1 or 2. And then I just simply substitute the value of n, and I have my answer. Good? Not too fast? Yes, this is still boring, so I'm glossing over it. Yes? Not too fast. Good. Then we have something that is called cumulative distribution. I cannot tell you what's its main use. If it's a discrete random variable, it's definitely very useful when you have continuous random variables, because it ends up being the antiderivative. It ends up being the fundamental theorem of calculus. Okay, but in general, the cumulative distribution, it's just the probability that x is less than or equal to a. Okay, so that means it's the summation of all the probabilities of values that are less than this particular real value a. So we can actually figure out the cumulative distribution, for instance, for this example. So x has the mass function, let's say, probability of 1 is 1/4, of 2 it's 1/2, of 3 it's 1/8, and of 4 it's also 1/8. Okay, so then you can see what will happen. If a is, I mean, we can even draw it just in case. So what's happening is that we are picking up pebbles as we are sweeping through the x-axis. Okay, so here are the values of interest are, I believe, 1, 2, 3, 4. Am I right? Yes, 4, right? That's right. And so what happens is that if I select this as my border, This is f, this is my a, this is f x at a. Now, there are no values for which the probability is non-negative, right? So that means that this is just 0. You all see that, guys? Because I don't pick up any values. No value of x that can contribute to probability is below a. Now, what happens? What happens if I select my value over here or at 1? So if this is my a, then fx of a will be simply just the probability of 1. If I were to select my a at or beyond 2, but below 3, then this is my new a, then the probability of that new a will be the probability of 1 plus the probability of 2, and so forth, right? Once I reach 4 and go anywhere beyond 4, the probability is adding up every event here, so the probability will be 1. Good? This is what's happening here. So 0, then I gain 1/4 because I pass up to 1. Then I gained 1/4 and 1/2 because I went beyond 2. And then onwards until I get to 4. And here is the steps. You can see that at 1, first time I grab 1, that's when a is equal to 1. Then I jump. And then I don't pick anything until I reach 2. And after 4, I just continue moving at a flat line, which is at altitude 1. Now, this is first very deep idea. Okay, why random variables are so interesting is that you can calculate averages, which is what I call correct stereotype. Okay, so how do you stereotype correctly? When you make generalizations, usually about anything, that's perhaps, if it's correct generalization, it's about the expected value. Okay, the average of something. So let's consider the situation. Suppose you play a game, and you want to know what happens as a result of playing that game habitually, right? So one game would be, some people tell you, do not drink because that will make your liver go bad, right? But then you probably know some people that just drink and their livers are good. So is it a contradiction, right? So expected value is supposed to tell you what happens if you make a habit of something, if you do it again, 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 and again. Should you play the lottery? One time, I don't know. But I can tell you what will happen if you play the lottery all the time, habitually. Good? And why is that going to work? Because of this idea, guys. So let's suppose that we play a game, and in the game there are payoffs x1 all the way to xk. So I just made it for a moment finitely many payoffs. Can you imagine, right? So k could be a million payoffs, different monetary outcomes or different things that you can assign value for. Now, what happens if you played a large number of games, n number of games, where n is huge, right? And huge is very, very relative term. We're going to see interesting paradoxes. Huge just means, you know, bigger and bigger and bigger, right? What will I see happening? So this is what will happen. You see, if I play n games, some of those games have created payoffs x1. Some of those games have given me payoffs x2. Some of them have given me payoffs x3, x4, all the way to xk. Now I can average what's my winning per game, right? So I played n games, so I divide by n. Now I can average in such a way where I add up all the games in which I got payment x1. So the total number of money from such games is x1 times the number of games that contributed x1. Total number of games that contributed x2 times x2 is the total money I got from those games, and so on and so forth. So far understood? You understand what I do, guys? Imagine you have a huge table and the games are, and then you organize this table based on the payment, right? So you see game 1, game 2, game 3, but then you just look into the column where you see how much you earned in that game, and then you order the computer to group the games based on payment X1, based off payoff X2, and so on and so forth. Yes, and then you can tally, you can just see how much money you have earned for all the games by saying score X1 multiplied by total number of games that produce that score. X2 multiplied by total number of games that produce the X2 score. Clear? That's very important, guys. I have to because this is the new concept finally, right? So we're moving into this new concept. I have to be sure you get it. And so what happens? Look at it. This is the summation. This is the average payoff per game that you have received. Agreed? Now look at this, guys. What happens if n is huge? If n is huge, it's as if I take limit as n goes to infinity. Now it will be the summation of xj, and you have this ratio, n of x equal to xj divided by n. But what does this ratio equal to? Look at this ratio. What is that approaching? Please type in the comments if you see. What is that limit approaching? That's what I was asking. So if you don't see it, then you do not understand. What is probability, guys? Probability is this idea that you see when we say that payoffs x1, x2, x3 and onwards, they have a probability of occurring. What is that probability we have? We have this running frequency. Do you remember? That probability is the number of times they occur divided by total number of times, right? So when you say a coin is fair, it means it has no preference to land on heads or tails. That means what? That means that if you toss the coin 1 billion times, you will see that half of the times the coin came up heads. Good. It says my connection is unstable. Is it true? Unstable? Or is it just me? Well, here you go. Okay. Are you following, guys? You have to really think deeply about what probability means. It's this running sequence, right? You remember we talked about it, right? It's just how many, if I take the total number of successes divided by total number of trials, that ratio tends to a number, right? So what is this? What is this situation? N of x equal to xj. This is let's say if I consider this to be a success, to get payoff xj divided by total number of trials, its limit is the probability of xj. You agree? Because that's the chances, that's how frequently it occurs. Probability is measuring frequency of occurrence. So what's the easiest way to empirically measure frequency of occurrence is to take to take n to be very large, right? To just repeat the experiment again and again and again and see how many of those experiments produce success. Yes? So that's the probability. It's very important, guys. Do you see we get this formula? That's the formula for expected value. If you don't have a sense for it, then whatever follows will not surprise or will not interest and will not make sense. Yes? That's the definition of expected value. I try to explain why that definition is supposed to be what it is. So expected value of the random variable x, it's just the summation of all the xj multiplied by their probabilities. And we see that that must be the right definition from this heuristic idea, right? Probability is a sort of philosophy for us, running frequency. We believe that things that have probability, we will see that the ratio of successes divided by total number of trials will tend to a certain number. Good. In other words, nature balances itself out, will show its preference if you allow it a lot of opportunity. Here is an example, guys. If you understood it, could you please tell me what's the expected, what's your average win per game? If you get $1, if you roll a dice, you get $1 if it comes up 1, $2 if it comes up 2, 3 if it comes if the die comes up 3, and so on and so forth. Could you calculate, please, your average payoff per game? Expected value can be any number, of course. It's not probability, it's just the average of, it's the average win per game. If you think of it as gambling, it's the average amount of money you will get per game if you play many, many games. Okay? So you understood what I asked, guys? Yes, I want you to tell me what's the expected payoff if you roll a fair dice. If you roll a fair die, I'm sorry, and the payoff is the denomination of the die. Okay, thank you, Ben. Thank you, Aaron. Come on, guys, a few more just to be sure that you can calculate. Okay, Alan. Okay, Fno, you can, that's correct, but you can come up with a quick formula for it, yes? 1 plus 2 plus 3 plus 4 plus 5 plus 6, what's the summation? And again, guys, you're kind of unfriendly today, right? I see very few faces, right? It's not nice. Here is that summation. It is, as whoever replied, it is 7 over 2. Yes? 7 over 2. Why is it 7 over 2? Because you can see that the expected value is $1 times probability of 1/6 to earn it, $2 times probability of 1/6 to earn it, $3 times probability of 1/6 to earn it, so on and so forth. Yes? So it's 1 over 6 times the summation of k, where k goes from 1 to 6. And that summation is simply 6 times 7 over 2 times 1 over 6. It's just 7 over 2. Good? Now, here is a question, guys. I'm going to offer you this game. Suppose that when a fair die is rolled, 1 second, let's see what's not adding 6 over 1/6. What do you mean? It's just now that you have, I just factored out 1/6 out of the summation. I calculated the sum of k, that's 6 times 7 over 2. And then when I multiply by 1 over 6, it's outside here. I cross out the 6. So I'm just left with 7 over 2, or some people wrote 3.5. Good? Now, good. Now here is, I'm going to make you this offer, guys. Would you play it if I did? So a fair die will be rolled. You will win $6 if the die comes up 6, and you lose $1 if the die comes up with any other number. Would you play this game? And how about playing it for 100, well, for 1,000,000 rounds? Would you play 1,000,000 games like this? Okay, some people say yes, yes. Well, let's now. Why would you want to play? What's so great about this game? And of course, we'll ask afterwards other questions relating to such situations. Expected value is greater than 0, Sarah. Okay, interesting. You ready, guys? Let's talk about this question. Let's see what happens here. So what is my random variable? My random variable is either -1 or 6, with -1 having probability of 5/6 and 6 having the probability of 1/6. So what I have here is simply the expected value is 1 minus 5/6, which is 1/6. What does this 1/6 mean? Would anybody interpret it? So I said expected value is equal to 1 divided by 6. What it means is very good. You get on average, you understand, guys? So the game is not regular. Sometimes you lose $1, sometimes you win $1. But if you play many games, what does the average tell you? That your sense of that average is that, well, it's as if you're just regularly getting 1/6 of $1 per game. Yes? 1/6 of $1 per game. Some of you said that you will play here. So that means that if you play 1,000,000 games, then on average, well, not on average, if you play 1,000,000 games, it's as if each game contributes 1/6 of $1. So you'll get $1,000,000 divided by 6, which is not a bad amount of money. Yes? But of course, there are other ideas that must be involved. We'll delay them, right? I mean, we just noticed expected value is positive, and some of you right away jumped to the conclusion they should play this game. Yes? So a game of Russian roulette is...
Professor,
Go ahead.
can you again go back to the last example?
Yes, I'm there.
I mean, the one before this one.
Before this one.
Yes.
You mean about yes, this one with $1 and $2 and whatnot? Yes.
Yes. I mean, like if you see the summation signs, k goes from 1 to 6.
Yes.
So I was wondering, like, if we do it like 1, 2, 3, 4, 5, 6, then it should be 21 by 6.
Yes.
But we are getting here 7 by 2.
Well.
Oh no! I made a mistake. Yeah, no, 21 by 6 is actually 7 by 2. Yeah. Thank you.
Yeah, well, good. It just what do you just the summation of the k is what? It's 6 times 7/2. It's this thing.
Yes.
Right? But there is a 1/6 over here. So what I do is I don't even, I don't multiply anything. I just cancel the 6. I have 7/2 in it.
Yeah, my bad. Sorry.
No worries. So here is now a game of Russian roulette, guys. You all know how to play it, right? It always this question reminds me of the movie Deer Hunter. Have you ever watched this movie? It's with, yes, some people have. I mean, I don't know, right? It's not a bad American movie. Do you agree? Yes. You see, you haven't watched, guys, right? I know one person is saying yes, but what about the rest of you? You don't watch your classics. What are you watching? My God. Yes, Robert De Niro. TikToks, yes. I have to show you. I have to introduce that thing to you, right? I have to teach you American movies, or even those, right? We have to watch American movies together. There are some very good ones. All right, so Russian roulette. So how do you play it? Well, normally you have a revolver, and in the revolver you have 7 chambers. You place 1 bullet in that drum, and then you roll the drum before you press the trigger. Okay, so you might, if you want to schedule, like in the Deer Hunter, if you want to schedule a session of Russian roulettes, you need to know how long will the game last, how many rounds will it last before the game is over. Yes, so that you can plan your entertainment. So how long on average will that game last, guys? Can you calculate? Help the Vietnamese understand that so they can schedule it in their casinos. How many rounds will the game last? You can even guess it, guys. You see, you might think about it, and you might realize what's the answer immediately. Exactly, 7. Jack. Yes, that's funny. But you see, if before shooting you always roll the drum, the chances that you will be shot is 1 out of 7. Do you agree? Which already, without any calculations, means that that you will hear a shot every 7 rounds on average. So that's the answer then, right? 7 rounds. Okay, let's verify that it's indeed true, guys. You see, we kind of, without any calculation, by pure intuition, by pure just understanding what probability means, 1 out of 7, which means on average, every 7 rounds you hear a shot. Good. Now, how can we verify that this is indeed the case? Here is, it's much more difficult, of course, to do the algebra, but we will nonetheless compare it, as it's interesting to make such comparisons. So here we have the situation, guys. So X is 1, 2, 3. That's how many rounds the game lasts, right? And then the probability that X is over on the nth round is a geometric sequence term. It's 6 over 7 to the power of n-1, which means you did not hear a shot in the first n-1 rounds, times 1 over 7. And that means the first time you hear the shot. Good? So, and then the expected value is simply the summation of n of this outcome multiplied by this, you see. So how do you do that, guys? You can imagine a giant table, and you recorded how many games were over after 1 round, how many were over after 2 rounds, 3 rounds, etc. Right? So then you would realize that if you tally up the games that are over with, let's say, 7 rounds, it will the ratio of those games in your table will be given by this probability. Okay, make sense? So what you're doing when you're doing it, instead of dividing money, you're dividing rounds per games, right? So some games bring a lot of rounds and some games bring very few. So now, again, Deer Hunter, guys, check it out. It's not a bad movie, right? Maybe it should be an extra credit assignment. Watch Deer Hunter. So here is that summation, guys. How can I find that summation? Look at it. The beauty of combinatorics is that I look at the summation, and without doing any thinking, I right away know the answer is 7. Isn't it nice? Right? So you have this infinite series and you think the answer is right away 7, so you didn't bother doing anything. You feel so easy and free. But let's do it still. Let's actually calculate it just to be sure that I'm not lying to you. So first, let's remember how we calculate geometric series, right? So just let's pick x to the power of n-1, and that's equal to g. That's a geometric series. So we can use that fractal idea that we mentioned here, right? So we have 1 plus x squared, etc. So that's equal to 1 plus x, and in parentheses, what I factored out of, it's just g. So g is equal to 1 plus x times g. Take it, you understand, guys? It's like what we did when we reviewed calculus, right? Remember, you have this regularity. It's 1 plus x squared, etc. And then I realize I factor out x from after the 1, and I see g. So it's 1 plus x times g, and I get a very easy equation. So g is equal to 1 plus x times g. Anybody needs more elaboration on that or not? Please let me know, guys, if I'm not moving too fast. Okay. Not too fast. Great. Now, that means that g is equal to 1 over 1 minus x. That's the summation. Good. Now, what do I do about this situation? H is more like my situation over here. You see, I'm just making 6 over 7 my x. So this is h equal to n times x to the n minus 1. Yes? And how do I sum such a series? Well, I can still break it apart. It's best to keep it in this form, but I will write it as n minus 1 times x to the n minus 1 plus x to the n minus 1. Let me show you just in case you are not seeing it in slow motion. This is what we're doing, guys. How do I sum up? So we know that this type of series or let's actually write it in this form. Let's write it like this. We know that this is equal to 1 over 1 minus x, yes? For all values of x that are smaller than 1, there is no dispute. Now we're interested in summing up this type of series. Good? What is this? And so what I decide to do here is I will write it as the summation. So n I can write as n minus 1 plus 1 times x to the n minus 1. One second. Yeah, okay. Good. So you understand, I just split the n into n minus 1 plus 1, and then I distribute the x to the n minus 1 through it. So this is the summation where n is 1 to infinity of n minus 1 times x to the n minus 1 plus x to the n minus 1. You see? Now the summation, I can move it in here and in here. So what do I get? I get this summation plus the summation of x to the n minus 1. We already know it's 1 over 1 minus x. Good? And then what is the summation that I have over here? Well, I can just relabel it. I can write it in terms of a different number. I can say m is equal to n minus 1. So it's really where m starts, where it's at 0 doesn't matter. So I might start m at 1 to infinity of m x to the power of m plus 1 over 1 minus x. All right, guys, any questions at this stage? Do you understand what I do? I'm just making the expression look like the original. Everybody understands? Or if not, let me know. I might be too fast today, who knows? Good. So do you see what this is? This looks like h. Look how similar it is to h, except I need to factor out an x. So if I factor out the x, I see that I have here x times h plus 1 over 1 minus x. Here it is. And then simply move things around. Just take h minus x times h. So what you have is 1 minus x multiplied by h is equal to 1 over 1 minus x, which implies that h is equal to 1 over 1 minus x squared. Good? Most importantly, guys, understand the idea, right? The calculations you should be able to figure yourself. What's the idea? The idea is that I'm still trying to do the same thing I did for the geometric series. I'm trying to see the full sum contained within itself. Here is the answer then, guys, right? So what's the situation? we now know that that this series, look at it, it's x here is 6 over 7. So what I have here is I have 1 over 1 minus 6 over 7 squared multiplied by 1 over 7 is the expected value. Now what is the number here? That the number over here is simply 1 over 7 squared. So it's 1 over 7 squared multiplied by 7. So it's 1 over 7, which is 7, just as we predicted, right? So we knew, some of you knew, the answer will be 7 without doing any calculation. And we just verified it algebraically, I suppose. Good? That's pretty nice, right, guys? Good. Okay, so here there is a small interruption in the development of expected value ideas. Hopefully I'll go through it fast. I mean, it's a bit uninteresting. So it's properties of the cumulative distribution function, okay? So let's suppose that we take P, and P is a map from the sample space. Oh, you know what? Let's see if I can. Do I need it before I get to my today's point? Before we interrupt, we will return to the top in a moment. Perhaps let's try to push the expected value thing. So guys, remember that in that game where you lose $1 if you get 1 through 5, and you win $6 if you get 6, and many of you decided that well, I hope many, I'm not sure, but some people decided the expected value is positive and therefore they're in. Yes, so here is an interesting question here. It's called St. Petersburg paradox. Okay, so suppose you go into a casino, and this is what's going to happen in this casino. A fair coin will be tossed until the first time when it comes up heads. And if you get heads on the first trial, you get $2. If it's on the second trial, you get $4 or 2 squared. Third is 2 cubed. You know, if it's on the 16th number, it's going to be 2 to the power of $16 that you get. You understand? And in general, if the first time is on the nth trial, you are paid 2 to the power of n dollars. Good? Would you pay $1 million to participate in this game? And of course, you might say you don't have $1 million, but imagine. But what happens in this game is that you can get indefinite loan, right? You can get a loan each time you play the game, and you only have to pay it once you decide to leave the casino. Will you play this game? Why nope? No. Yes, but if it lands on the first, then it will be. Yes, but you see, you're risking. Here is something you are misunderstanding, guys. You can play a second game, third game, fourth game, 10th game, million game. You see, each time you play a game, you get in debt. But is it worth getting into the debt? Calculate. How much will you win per game? on average, right? So you were motivated before by expected value, correct? Now, first question is naturally what's the expected value? Because expected value tells you on average how much you win per game. And if you know that average, that means if you play many games, the result of each game will be the same as if it's the average. You understand? So if you play if you buy lottery tickets, what's the problem? If you buy one or two lottery tickets, it's unpredictable. But if you buy lottery tickets all the time, it's going to be essentially as if you're losing $1, right? Maybe 99 cents for each time you buy the lottery ticket. And that's why it's not worth playing the lottery regularly. As a habit, you will just be paying 99 cents. What about this game? If you play it regularly, in other words, if you're taking loans and you take it again and again and again, is it worth playing this game? Remember, the payoff is always minus $1 million because you lose $1 million for each round. Jack, I see you're trying to exercise my demons, huh? You can do it, guys. I believe in you. Here are your payments, right? Payments are 2 to the 1, 2 to the 2, 2 to the 3, each of them minus $1 million, of course, right? It's very simple. Play. Okay, good. Alan is saying play. You see? Why, Alan, do you think play? Yes, you have to play a lot. That's the question. Yes. Now Fnu says play. Interesting, guys. I want you to be drawn. I mean, come on, guys. Don't be sleeping. You have unlimited credit. That's true. Yes, you can keep on playing, unlimited credit. You just have to pay once you leave the casino. All right. Calculate it together, I guess. Or yeah, let's do it together. Very simply, guys, what are the possible payoffs? The payoffs are 2 to the 1 minus 10 to the 6, or 2 to the 2 minus 10 to the 6, or in general, 2 to the n minus 10 to the 6. That's because for each game, you have to pay the entrance fee, which is 10 to the 6. Yes? So that's the payoff. So then what's the expected value? The expected value is 2 to the n minus 10 to the 6 times the probability of getting that payoff. What's the probability of getting 2 to the power of n dollars? It means it's 1/2 to the power of n. Do you agree? Because it's first is tail, probability is 1/2. Second is tail, probability is 1/2. All the way to n minus 1 throw of the coin is tail, and then the last is head. So it's 1 divided by 2 to the n. Do you agree? That's the expression that will calculate my expected value, my average win per game. It's very important for you guys to think why that is the average win per game. You have to understand that. Otherwise, there is nothing surprising or meaningful about it. So what do we get? If I multiply 1/2 to the n times this expression, it's just 1. So the summation is of 1 minus 10 to the 6 over 2 to the n. And if I just sum the series this way, if I don't go to infinity there, it's just summation of 1 minus the summation of 10 to the 6 over 10 to the n, which is going to infinity. You can see that this is not converging. This number is going to eventually be close to 1, right? Because 10 to the 6 divided by 2 to the n is a small number. So this number is not going to 0. So as you play more and more games, this infinity means that you will start to earn more and more money per game. You understand? If you play lots and lots and lots of games, you will start earning money. And then you see that your average per game is not even a stable positive number. It's going to approach infinity per game. You understand? So on average, if you play this game, you win infinitely many dollars. What it means in practice, I suppose, if you play many games, then you will see that your average earning per game is just growing, right? So at some point you will see that you play enough and you see, wow, I'm making $1 million every time I play this game on average, and later I'm making billion every time I play this game if I play it long enough. You understand? So do you now want to play the game? Yes? Type in the comments, guys. I think we are very sleepy today. Maybe it's my fault, but I want to see a lot of you. So let's see. Sarah now says yes. Elise says yes. Ben says yes. Jennifer, yes. Yes, well, if we have limited credit, why? I mean, you want to pay the authorities or the casino? Abdel says it looks like a scam. You don't trust me, I think, Abdel. Good. Now, is it meaningful to play this game? Let's now see something else about it. Okay, Aaron says time opportunity cost is not worth it. You see? Now, let's try to understand. Well, you understand, guys, if you play many games, right? But you think about it, right, guys? You see, if I told you, do you want to make $1 million? I just tell you, okay, go and build me houses and I'll pay you $1 per day. After a while, I mean, after millions of days, you'll get $1 million for sure, right? It's how fast. You see, the expected value is not the only thing that you should be concerned with, guys. Don't rush and say, oh, expected value is huge. Maybe, but you know, how quickly is this going to happen? You understand? You are not an infinite being. You don't have infinite amount of time to wait, and even the universe isn't. Okay, how long will you have to wait until you see the fruits of your labor of playing this game? Let's try to see it, guys. So here, to explain, I will modify the St. Petersburg paradox. Are you ready? So I am going to make, like FNU is suggested, I'm going to not quite like FNU suggested. I'm not going to make limited credit, but I'm going to limit the amount of money you will make. I will truncate it. You understand? I will not allow you to make more than a certain amount of money. And that will help you see how quickly are the scores gathered, right? So suppose in this situation, the game is as before, but you only have the same rules until you reach the number n, capital N, which is the cap, right? Let's say you are not allowed to, you know, if the coin lands on heads more than 100 times, let's say, afterwards it's not going to increase. You understand? So up to this n, you have the same earning as before. But if the coin lands on heads for the first time after this n, you simply get 2 to the power of capital N plus 1 and no more. You understand? So that's a cap. It's not if it's, let's say, if the cap is at 100 and the coin lands on heads on the 107th time, you just get 2 to the power of 101 and no more. You understand? Yes? And then let's try to calculate when is this game becoming profitable. So same thing, you same price to pay for the game, which is 10 to the 6. And then let's see what happens. Now the probability is 1/2 to the n if n is less than capital N, and otherwise the probability of getting the biggest payoff, that's the biggest payoff possible. This is the probability. I calculated it, guys, and the probability is 1/2 to the power of capital N. Good. So then my expected value is the sum all the way to n of the payoffs times their probabilities plus the biggest payoff times this smallest probability. And if you calculate it, 10 to the 6 is your payment. I mean, each game that you play, you know, you're not just making, it's the net gain. You understand? What's the gain that you're making? You're paying $1 million to play each round. So right, so so it's the amount you earned minus the amount you paid for the game. So it's you're winning. Good. So look what happens, guys. If I sum this up, I hope it's just algebra, guys. You see, you can verify I'm right. This expected value is equal to capital N plus 2 minus 10 to the 6. And when is this summation bigger than, well, I said bigger than 1, or you can say bigger than 0, right? If you prefer, say it bigger than 0. Right, so I said that's basically when n is bigger than 10 to the 6 minus 1. Do you understand? So the expected value is only bigger than or equal to 1. The average, right, that you're making is bigger than 1 only if the number of times the coin is rolled before getting to be heads is allowed to be 1,000,000 minus 1. You understand? Can you imagine throwing a fair coin essentially 1,000,000 times and never observing heads before that happens? You see, the game only then becomes profitable. If this happens, that means, and this is your truncation, only with such astronomically strange and rare events can the game be profitable. Do you understand? If you don't truncate before, in other words, if you do not include such possibilities of very rare possibilities of the coin landing heads very, very far down the line, the game is not profitable. You're losing money. You see what I'm saying? Now, do you understand what's the probability of getting heads on the 10 to the power of 6 minus 1 trial for the first time? This means its probability, it's 1 over 2 to the 10 to the 6 minus 1. So this is about this many universes, guys, right? So the number 2 to the 10 to the 6 minus 1, it's about 10 to the 200,000 minus 82, but basically just 10 to the enormously many universes, based on estimations of how many atoms are in the universe or whatnot. You understand? This number is insanely large. So you will have to wait longer than the depth of this and many universes to come after this. I mean, you know, to observe the situation. So congratulations if you want to do that. You are then very, very patient, right? It is truly, you have to wait forever to see profits. So the game is absolutely not worth it. Even if you could simulate playing this game very rapidly, if you could play millions of games per second, it will not be worth it. You understand? Essentially, if you never have to pay, I mean, you might say, oh, sure, whatever, right? And just if you never have to pay, I mean, you just have bad credit. Right? It's very good to be bankrupt if you have to go to the hospital, because there's nothing they can take from you, I guess. So if that's your goal, then of course, by all means, play the game. Now let's talk about properties of the cumulative distribution. We don't have too much time, but let's begin a little bit. Yes, guys? Let's give a flavor of it. Jack, you don't seem very excited. Right? You don't like the flavor of that particular cake, do you? Well, it's okay. Once you eat worse cakes, you would enjoy this one. I envy you. Let's discuss exam questions. What's there to discuss about exam questions? Yes, you might be saying, how come they are so easy, right? Why did I not give you something interesting? That I understand. Question 11. Afterwards, maybe after in a few moments, we will discuss it, right? Let's say, so guys, a few moments and 3 minutes anyhow. So probability is a function from S to the interval between 0 and 1. And then we have increasing events. This is called increasing of a sequence of increasing events. And if E is the union of those events, then we can observe that the probability of E is the limit of the probabilities of En. It's a sort of continuity property of the probability function, okay? Do you see what I'm saying, guys? So we have increasing events, and if I want to calculate, they are increasing to E. In other words, as I grow them out, if I take the union of all of them, that would be E. The probability of E is the limit of the En. Why is that the case? Well, we can examine by, you can just represent it by this drawing, right? Here is E1, E2 is bigger than E1, E3 is bigger than E2. And this union is obviously not a disjoint union, but we can make it a disjoint union. You can see that if I go all the way to capital N, the union from N1 to capital N of those events is the same as the union of the events F. where F1 is E1 and F2 is the difference between E1 and E2. It's this thing. You see, it's so I take this disk, so I take the small disk and then the annulus and then union the next annulus and so on and so forth, right? It's just a diagram here. And so the probability, so this union is the same as the union of the FNs, and those are disjoint sets. You see, F1 is disjoint from F2, disjoint from F3 because those are those rings. Do you all see that? But it gives us the same thing. So what is the probability of E? The probability of E is the same as the probability of the union of the En, which is the same as the probability of the union of the Fn, but these are disjoint, so I can break it and make it into a summation. You can still follow, guys? It's a summation. And that summation just means limit as capital N goes to infinity of the sum of probabilities F sub n. And then I can take the summation and I can bring it back and make it a union. And that is simply the same as limit as n goes to infinity, the probability of the union n1 to capital N of En. But what is this? This is just E sub capital N. And the result is established. Yes? By your eyes, I see you understood every single word. Wonderful. So I will stop the recording, and then Fnu, you had questions about 11, so I will talk about that.